All right, properties of matter, day 5. Talked about density, or rather, you did density stuff, and you made a pretty graph, pretty colors. Okay, making plots. Whenever you make a plot, you're always going to do y versus x, so A versus B. So it's always what's on your y-axis versus your b. Doesn't always have to be that way, but it's generally the consensus, and so that's how you have to do your graphs. Don't forget your error bars. In your case, I will always tell you if you need error bars or not, and then you'll be able to include them. You won't have to draw them by hand unless it's on a test when you do have to do that. Most of the time, you'll have like a program do it for you. Slope of a trend line is rise over run. So if you remember from pre-algebra in high school or middle school, whenever you had it, it's y2 minus y1 over x2 minus x1. And it generally has some sort of significance. In our case, it's density because it's mass divided by volume. But for a case of velocity, it's displacement over time. Coefficient of static friction is the applied force divided by a static frictional force, etc. The point is, it actually has some physical meaning, and it can help us make predictions about the physical world. And that's why it's important to find the slope and everything that goes with it. Always use locations on the line for interpretation, not the actual data points. What I mean by that is this is a trend line, and in this trend line, it's basically finding the mean of all of your points. But if you were to find the slope based off of this line right here, the purple line, you're going to get, what, 1? But let's say you decided to use this point right here and this point right here. Well, and then you didn't go through 0, 0. You're going to have a much different line than what actually should be the slope. Sure, if you use this point and this point, you're going to get the same slope. But by using the points, you run the risk of getting a really, really bad idea of what your graph is actually doing. That's why you have to use the trend line, because, this one's above, almost by 1. Well, this one's almost below by 1, and so it's kind of mellowing out and evening out. Mass versus volume, slope is density, which is mass divided by volume. I will usually write this as a rho, which means density. We usually include 0, 0, because if you have 0 mass, you're going to have 0 volume, classically. A black hole doesn't quite obey that law of physics. Or really, it obeys the law of physics, but it doesn't exactly obey what I just said here. But in classical mechanics, that's definitely true. All items made of the same material should have the same density and therefore should lie along the same line as you found before. And if the density of the object is greater than 1, it sinks, and less, it floats. So in this case, we had objects that sank above the red line, which is your water line, and objects below that floated. And the more interesting aspect of it is, let's say I wanted to put in vinegar or acetic acid. It's got a density... I should probably do it different. Let's exaggerate on this. It's got a density a little bit greater than 1. Well, if this is my acetic acid, vinegar, then some points, while they may sink in water, would float in vinegar, just because they're in between the two lines. And so if I made one, let's say, for oil, it might look like that, because oil is less dense than water, and these two guys would sink in oil but float in water. And so if you have all these trend lines for all these different liquids, you can kind of see based off of where the point is what that object's going to do in all of those fluids. So it's kind of good if you have multi-stage fluids all stacked on together. All right. Air propagation I pick up in the next video, which I actually did before this one because my system shut down on me in the middle of it. It was a mess. Long story. Okay, I'm trying this again because my computer froze up on me. So I think I'm going to have to split these and add these videos together. All right, air propagation. Whenever we have two or more values that have air and those values are being used for calculations, we need an estimate of how this air propagates. Let's say we're measuring the location of the sides of a cube. There we go. I like that. And so this is one side of the cube, and we have an error on where that cube is actually located. And it could be at this point right here. It could be measured here, or we can find it as far as here. So basically, these little dashed lines show you about where you're going to expect to find this side of my cube. Well, let's introduce the second side of the cube with the almost equal error. So we're going to assume that my lines here are perfect. And so now we can find it as high up as here, as far south as here. So really, what I can do, and this is where it froze up on me a lot. Please don't, why does it stop doing that? It does not like this. It whacks up a lot. Okay, so basically my cube can be found anywhere in this entire region where the actual size of said cube is right here. So by introducing a what's called new degree of freedom, i.e. another dimension, it expands on how much our error is. And if we have a third dimension, then we would have to do this all over again, but for a completely third side, which I don't really have the capability of drawing so much. But hopefully you get the picture. And each new dimension adds into how much your numbers can be off, because you're just adding another degree of freedom and adding another way where you can be off. Think of it as kind of measuring something on top of measuring something. For example, let's say you're trying to find the mass of a human that's 100 kilograms, and you got a plus or minus 1 error, and then you have to remass them on a different scale. Well, if you have the same error, you could have measured them as low as 99 the first time, and then you could measure them even lower the second time, or even higher. So each time you're going to add on to that error, if that makes any sense. Normally I'd look at your faces right now, but I can't. So, yeah. But that's kind of what it means to say error. Well, more or less what error propagation is. Every time you introduce some new calculated value, every time you introduce a new dimension, it's going to increase the amount of error that you have. And so that's why in density we use the second, no, we don't use the second smallest or second largest, we just use the largest and the smallest to try to encompass in that data. So to find density error, first you're going to find the averages of the mass and volume. And you write that as mass plus or minus sigma mass, sigma being your error. Same with volume. And then you calculate your average density from the average values. And then you have to do the max mass divided by max volume, min mass divided by min volume. I need to turn that off. Quit. There we go. Min mass divided by max volume, and then min mass divided by min volume. Then you, like I said, you're going to find the value that's furthest away from the average and find the difference, and that's the estimate of error. So let's do an example. Let's find the density of error. It's simple. 100 grams and a volume of 10. So my density, which I need to right here, is equal to mass divided by volume. And then there is a 100 grams divided by 10 milliliters to give me 10 grams per milliliter. And then I have to do max. So the max, that would be 101 grams divided by 11 milliliters. I don't think I can do this one in my head. No, I can't. 9.18. We're just going to say 9.2. So that'll be 9.2 grams per milliliter. And then we'll do max min. And so that's going to be 101 grams. God, all these freaking notifications are killing me. 101 grams. And then the minimum is going to be 9 milliliters. And that's going to give me 11.2. And then we'll do min. So that's going to give me 99 grams divided by 9 milliliters. And that's just going to give me 11. I still need to double check that in my calculator. I don't know why. And then we'll do min max, which is going to be 99 grams divided by 11 milliliters to give me a 9. All right, so which is furthest away from 10? Well, this is 1.2. That one's 1. That's only 0.2, so it looks like you win. And it's the difference between the two. So it's actually going to be 1.2. So you write this as 10 plus or minus 1.2 grams per milliliter. And that is it. That will be it. I will see you on Monday. Last lab on this section.